Hello. Today's talk is not only late by a week or two, but also one of the shortest that you will find on this channel. The reason is that this week's programme is essentially a version of the last one that you saw. That was the Discrete Fourier Transform, DFT. This time we have the Fast Fourier Transform, FFT. Needless to say, but I say it anyway, you would do well to watch the video for the DFT JavaScript programme that you saw last time, and of course the video on FFT that I created explaining how the process works. Links to both those videos below. The screen of the programme should be very familiar from the last programme. Apart from the fact that the button is now labelled FFT rather than DFT, there is only one difference, and that is the number of samples per time slot is now limited to a power of 2. A select box allows the user to choose 8, 16, 32, 64, 128 or 256 samples per time slot. That's because the Cooley-Tukey Fast Fourier Transform, as far as I can see, always has to have a power of 2 samples for the algorithm to work. I won't be going over the parts of the program that are essentially identical to the last one, as that would waste your time. Indeed, I'll only mention the meat and potatoes of the program itself, which is, of course, the Fast Fourier Transform. The FFT takes place over various stages, as represented by this diagram. The sample values of any particular time slot are represented at the left, and the diagonal coloured lines represent operations on those samples. The samples are then replaced by the FFT values, which gradually build up as parts of the diagram we're looking at move from left to right. The diagram shown has 8 samples per time slot, those 8 horizontal black lines. There are 3 stages in the calculation, colour-coded as red, green and blue, and the final FFT values are produced at the end of stage 3. If there had been 16 samples, there would have been 4 stages. 32 samples means 5 stages, and so on. One way of implementing these stages is to have an array of values for each stage. If there were 8 samples in each time slot and 3 stages, then we would use 3 arrays, numbered 0, 1 and 2. The raw samples go in array index 0, the final FFT values come out of array 2. Well, that's fine for 8 samples and 3 stages, but what if there are 1024 samples and 10 stages? As the size of the time slots increases, the number of arrays we need also increases, and the final values will be extracted at a different point along that line of arrays. It's actually easier to implement the different stages like this, with only 2 arrays. The sample values are placed in the array on the left, and the first stage turns those into values in the right-hand array. The next stage turns the values on the right into values stored on the left, and so on, backwards and forwards, like a bee in a bottle. At the end of the process, however many stages that is, the values will be either in the left-hand array or the right-hand one. We need only track where the values are being moved from and to. In fact, each of those arrays, left and right, will have to be 2 arrays, one for the real components of the values being calculated, one for the imaginary components. The initial samples are real numbers, of course, but at every stage these will be multiplied by complex numbers. When the sample values are copied into the left-hand array, the imaginary components are all set to 0. Here I have listed only the global variables that are new, not already present in the DFT version of the program. The 2 arrays, real and imag, will be turned into 2-dimensional arrays later. Numbits indicates the size of the time slot, insofar as an 8 sample time slot corresponds to 3 bits, a 16 sample time slot corresponds to 4 bits, 32 sample time slot corresponds to 5 bits, etc. We need to know this bit number when we come to first place the initial samples in the array. More on that later. The variables from and to indicate which column currently holds the values which are being processed and placed in the other. They oscillate between 0 and 1, so that if from is 0, then 2 will be 1, meaning that the values in column 0 are being processed into column 1. Then they swap places, and the next step processes the new values the other way. Finally, we need 2 global variables, RR and II, to indicate the real and imaginary parts of calculations. As with the DFT version of the program, clicking on the screen button doesn't call the FFT function directly, but calls setUpFFT, which lays the groundwork for the FFT function itself before calling it. Again, I've only included the parts that differ from the DFT version. At this point, both arrays real and imag are turned into two-dimensional arrays. The first dimension of each will contain either 0 or 1, representing the left and right sides of that diagram. Variable from will therefore either be 0 or 1, starting at 0 as you see. And variable to will be the other value, obtained by subtracting variable from 1. The local array bits is used to determine the value of num bits. This is done simply by comparing the value of capital N, the size of the time slot, with the contents of the array, and once we've found it, the index of the array gives the number of bits. The possible values of n starts at 8, i.e. 2 to the power of 3, so the minimum number of bits is 3. That's why the first three values in the array are 0. Those values just aren't applicable. Before we look at the main FFT function, there are three other functions I have to explain first. Here is a function multiply that does the complex equivalent of multiplying two values together. Of course, these values are specified by both a real component and an imaginary one, R1 and I1, R2 and I2. The whole calculation can be done in 2 lines of code. I've outlined the maths behind it underneath. This diagram shows a general butterfly with 2 input values on the left, designated by little a and b, and producing 2 output values on the right, capital A and B. In order to calculate the butterfly, we also need a value for omega, that thing that looks like a lowercase w, which depends on 2 values, k and capital N. Omega is given by the expression at the bottom of the screen, e to the power of minus 2i times pi times k divided by n. Of course, this will be a complex number, which is why the 2 output values, capital A and B, will also be complex numbers. The calculation is done by replacing that e to the power of I times something with the cosine whatever plus I times the sine of whatever version, the so-called cis version, CIS, of the power of e. Since lowercase b, the second input, might also be a complex number, this means that we are effectively multiplying 2 complex numbers. I mean, b starts off as a real number, that clearly isn't going to last long. The second term, multiplying the cis version of the angle by lowercase b, is used twice, and need only be calculated once. The function multiply gives us 2 values, rr and ii, so we just use the values twice to calculate both the output values. Of course, we don't refer to them as a and b. Both the input values are given as indices in the from part of the arrays, and the output values are the same indices in the to part of the arrays. The third small function is the one that takes a number, converts it to binary, reverses the digits, and then turns it back into a decimal value. The input samples aren't copied straight into the real and imag arrays. The order has to be changed, and this is how it's done. The conversion is fairly easy. Each bit is extracted in turn by seeing if the number is divisible by 2 or not. If it is, i.e. an even number, then the binary digit extracted is 0. Otherwise it's 1. The original value is num, and the reverse digit value is val. As num loses digits, val gains them. However, by determining the remainder when num is divided by 2, the digits are taken from the lower end of num. And as val is multiplied by 2 before the digit is added, the digits are placed on the higher end of val. This is how the digits are reversed, and the final result is a base 10 number. This is also the reason why we need to know how many bits there are involved in the number, so that we know how many digits to extract from one number and attach to the other. It's tempting simply to wait until num has been reduced to 0, then stop, but there may be extra zeros, so we need to keep going. This is the reason that we need num bits, and why it has to be a global variable. And now the pièce de résistance, the FFT function itself. In fact, I've only included part of the function, the part that differs from the equivalent function in the Discrete Fourier Transform program. First of all, the relevant samples are copied from the total input signal in array signal to the array real, column 0. This is the first set of values to be processed into column 1, and indeed the value of from has been set to 0 already in setup FFT. Note that the function reverse bin is called here to make sure that the samples are copied in the right order. Each of the steps in that butterfly diagram is then carried out by the next for loop, with the size of the groups increasing by a factor of 2 at every stage. The group size always starts at 2, to correspond to those butterflies that only span 2 adjacent lines, and increases up to the number of samples in the time slot. The inner for loop handles the overlapping butterflies within those groups, using half the size of the group as the division marker within that group. In the case of the first, smallest groups, of size 2, the halfway point is half of that, i.e. 1. The inner for loop can therefore only increase as long as it doesn't hit that value. So in practice, that means it stays at 0. This is why there are no overlapping butterflies at the first stage. On the other hand, once the group size has hit, say, 8, then the halfway point is 4, and the inner for loop will go up to just under that, i.e. from 0 to 3. This means for that group, there will be overlapping butterflies, line 0 with line 4, line 1 with line 5, line 2 with line 6, and line 3 with line 7. You can see the call to function butterfly in the midst of all that lot, the 2 lines providing the indices of the inputs and the outputs in arrays real and imag, are given by variables f, and f plus half the group size. The final 2 parameters define the value produced for omega and correspond to k and n in the individual butterfly diagram. You really need to sit down with the whole butterfly diagram containing all the steps and marked up with the correct omega values at each point in order to understand fully how the code ties in with the diagram itself. That was a very whistle-stop tour of the program, but as I said before, it is really just a variation on the JavaScript implementation of the DFT program that you saw last time. I trust that you will try it with the same test data as you did with the previous program, just to make sure that it produces the same results. You might like to add counters to each of the programs that clock up the number of calculations needed. By calculations, I mean the number of times e to the power of something is calculated. It should be proportional to the square of the number of samples in the time slot for the DFT, but considerably smaller than that for the FFT. The difference becoming more and more noticeable as the number of samples increases. Now that we have processed our signal into frequency spectra, it's about time we did a bit of automatic recognition using them. So next time, I shall introduce you to the concept of dynamic time warping. Goodbye.